Hello and welcome to this GLOBEClaritas video presentation. I'm going to use the GLOBEClaritas Wavelet tutorial to demonstrate the capabilities of the Wavelet application from the GLOBEClaritas software. So I'll also work through the presentation that we have with the tutorial just to sort of highlight certain areas. Just a little bit about the dataset I'm going to be playing with today. It's going to use some seismic data and the wavelet or Farfield signature from the 05CM Crown Minerals 2005 survey, which was supplied to us by the NZP&M Group, the Ministry of Business, Innovation and Employment, New Zealand. One of the beauties of working in New Zealand is there's lots of freely available data that you can download from NZP&M's website. So the signature is supplied to us in 0.5 millisecond sample rate in nucleus format ASCII number dumper. We model the receiver ghost in the wavelet application, and we also create a debubbling filter again within the wavelet application that can be applied to the signature. We can read either nucleus, Gundelf, native ASCII files or SegWide data directly into the wavelet application. Any other ASCII format would need to be reformatted for the wavelet application to read it into a sort of a column format with a time and amplitude value. And then, or you can also take that sort of ASCII format and read it into the XAS SegWide utility if needed. So we read that nucleus format ASCII file into the wavelet application, and we do that by starting the wavelet from the launcher, define a name for the wavelet session file, and then clicking on the new button when the wavelet application is up and running. So at this point I will go to the GLOBEClaritas and start with the wavelet application. So if we go to the wavelets tab of the launcher, click on wavelet, and create a session file called video for this. And then basically I can select from the data folder the relevant, or from the wavelet folder, sorry, the relevant input dataset, which in this case is the MGC 4140 cubic inch dataset. So I'll cancel that because I've already got that selected. I define the file type, and in this case it's nucleus, and I give the dataset a short name. So click OK, loads the wavelet in, and you can see basically it's set the time 0 where it's needed to be. We've got the wavelet itself, or the Farfield signature, which is just over 300 milliseconds long. We have an amplitude spectra and a phase spectra of the filter. The first thing I will do is create a receiver ghost, which I can then convolve with the input Farfield signature. So if I go to the create option and select spike wavelet, I'll define the sample rate to match my input Farfield signature at 0.5 milliseconds, 100 millisecond wavelet for this, and then I'll have spikes created at a time of 0 and 8 milliseconds. And my spike at 0 will have an amplitude of 1, and my spike at 8 milliseconds will have an amplitude of minus 0.9 to indicate a subtle decrease in amplitudes, with the energy from the source having travelled through the water and then been reflected off the water bottom, with some of the noise still transmitting through the water bottom, and a lot. So click OK, and then you can see the resulting wavelet. Just stretch that out a little bit. So you can see that we've got the two spikes, and then we've also can see the amplitude spectra shows the notches that we're expecting from that ghost reflector. So I can now take my input Farfield signature, my spike or my ghost receiver, and I can convolve those two together to get my Farfield signature with ghost. That results in that sort of wavelet there. The other thing I might want to do to this data is create a debubbling operator. So again, I can take my Farfield signature with ghost in the unary filter, so i.e. using my input data and creating something from that rather than convolving or matching or merging something. So go to the unary filter, select my Farfield sig with ghost, decon operator, 0 to 500, 224, click OK. And then I can take that resulting decon operator that will hopefully debubble my input data set and convolve it with my Farfield signature and ghost. So I take that, Farfield signature decon operator, and convolve, give it a suitable name. Now we have our Farfield signature with ghost and debubbling applied. Before we create our minimum phase equivalents and our matching filters, we need to basically take our Farfield signature, which is at 0.5 millisecond sample rate, and match it to the sample rate of the data we're going to apply the matching filter to, and we take it out of the wavelet application. So if I take my Farfield signature, ghost and debubble, and then I'm going to resample to 2 milliseconds, 2.0. Now I'll use the inbuilt anti-alias filters, but you can design your own Butterworth filter to cope with the aliasing if that's your preferred method. But for ease in this demonstration, I'll just use the inbuilt ones. Click OK. And now we have our signature ghost debubble resampled to 2 milliseconds. You can see we're now at 250 Hertz, our maximum frequency. So I can then take that wavelet and create a minimum phase or 0 phase equivalent to that. I'm going to do minimum phase and just call it MPEQ. Keep the name slightly shorter. Slide down, have a look at what that looks like. So yeah, we can see that we've lost our sort of precursor before time 0, and the energy of the wavelet sort of pushed up into the sort of start of the wavelet a little more. The amplitude spectra looks very similar. There's little change to that, but our phase spectra now sort of looks very minimum phase, so kicks off at 0 phase point and then just basically rotates around the 0 phase line back to 0 at the end. So I can now take my resampled Farfield ghost and debub and my minimum phase equivalent and create a matching filter. So it'll come up with a little warning suggesting that in some cases I may want to apply Butterworth filter to filter out some noise from the matching filter. Generally, this doesn't seem to be a problem, so shouldn't be something you need to do. And that's our matching filter. So if we then take our matching filter, or our resampled ghost and debubble wavelet, and our matching filter, and convolve those two together, we get our resulting minimum phase wavelet. It's a little hard to see because we've basically ended up with an output wavelet that's the same length as the combination of the input matching filter and the minimum phase or the ghost Farfield sig debubbled wavelet. So if we zoom in around the area we're interested, out to around about 300 milliseconds, that's the length of the wavelet when we're dealing with it before the matching filter. We've now got our resulting minimum phase version of our Farfield signature, which looks pretty good. It'd be useful to compare it with our input data. So if we go up to our debug and resample dataset, I can delete it and then undelete it to sort of put it next to the resulting minimum phase equivalent. And the wavelet looks pretty good. So the amplitude spectras look the same pretty much, but we can see from the phase spectra that it's looking more minimum phase on that wavelet with the matching filter applied. So when we're happy with the matching filter, we can basically write it out into the GLOBEClaritas project and apply it to our data. So we have two ways of doing that. We can select the relevant wavelet and select output from the list of drop-down operators and give it a name, in phase match .wts. Okay, and that's written that out. Or we can select output. So if we right mouse button click on the wavelet itself, then we can select output as what we want to do and write it out from there. Claritas launcher and flows, job files. We can then select the example job in here that basically applies the near trace, the signature to the near trace. So at the moment I've got an option to apply both, test it both for 0 and minimum phase. I'll just change it to 2 repeats and select the minimum phase option. And okay that, and basically what we'll do is it will bring up a panel with no minimum phase filter, matching filter applied, and one with on the XView module. So if I click run, right, so you can see that we've now basically got 2 panels, one with and without minimum phase equivalent applied. So if I zoom in over an area, over this flat area here, no desig, go all panels, we've got no desig and desig applied. So we've got no tone shift introduced, which is great. That's one of the hazards with creating designature operators. But we can see that basically sort of pushing more energy further forward in the wavelet. So it's sort of a typical minimum phase response that we'd expect. So it's all looking pretty good, working nicely. So that's generally how to use our wavelet application. It's quite a simple tool. It has the advantage of being able to label each of your outputs so you know exactly what you're doing. Well, you can take screen grabs of each of these sort of operators and put them into any report or documentation you want to create. When you exit out, we can save the session parameters such that should you want to restart it, you can just pick up that relevant session file and it'll recreate all these inputs as they currently exist, enabling you to start from where you were and refine your approach. So hopefully you found this little video useful, and if you have any questions about Wavelet or GLOBEClaritas, please don't hesitate to contact claritas.support@gns.cri.nz, or if you want to make an inquiry about purchasing the software, claritas.sales@gns.cri.nz. Thank you for your time and goodbye.